Hello young minds, welcome to All Force e-learning program. Now in this session, we will deduce a formula for the electric field due to a non-conducting charged solid sphere, right? So today's topic is electric field due to a non-conducting charged solid sphere. Non-conducting charged solid sphere. It is due to the electric field due to a non-conducting sphere. You know, sometimes you can spell it as insulating sphere, dielectric charged sphere, non-conducting or insulating or dielectric charged solid sphere. Now for such thing, what would be the electric field at various points there? Okay, right? So before going to this, let's have a preview. Let's have the review of what we have covered till date and the things which are helpful for the deduction of this formula here. So I was telling you, charge fundamental property. Every charge produces a field. In the field there are lines of force. Field has strength. The field strength, the characteristic property of the field, electric field intensity. So electric field intensity is force per unit charge. E is F by Q, right? So we have to deduce a formula for the electric field intensity for this charge distribution, right? Now electric field, we have covered electric field due to point charge, due to a dipole, multiple charges. For these things we have made use of Coulomb's law. Coulomb's law is applicable for point charges, discrete isolated point charges only. You cannot use Coulomb's law for charge distribution. Charge distribution distributed on a line, on a sheet, on a surface, charge inside in a sphere, over the surface of a sphere. So for all this you cannot apply Coulomb's law. For this you need to learn Gauss law. You have to apply Gauss law. So to explain Gauss law, first electric flux, the measure of number of lines of force per unit area, right? Flux phi, flux density, electric flux density E. So E is equal to phi by A, electric flux density. Electric flux density or electric field intensity, both being the same. So cross multiplying, I get flux as E dot A. For uniform field, it is directly E dot A, it is equal to EA cos theta. For uniform field, I can write flux as EA cos theta. But if it is non-uniform electric field varying from point to point, the small flux through a small area element is E dot ds. So the total flux integral d phi is integral of E dot ds. So by definition, the total flux through a surface, the total flux through the enclosure is integral of E dot ds. The surface integral of E dot ds it is. Well, next Gauss law. According to Gauss law, the total flux through a Gaussian surface. First you have to imagine a Gaussian surface enclosing the charge whose electric field you want to find out. So the electric flux through the Gaussian surface is charge enclosed inside the Gaussian surface by epsilon. Now putting these two, the mathematical form of Gauss law of electrostatics. So it is the surface integral of E dot ds is charge inside by epsilon naught, right? So these are the basic points which we need to derive the electric field due to a solid sphere. Now, so coming to our topic, is it? I am given with a solid sphere, non-conducting, a bad conductor, insulator, or a dielectric sphere it is, right? Well, it is charged uniformly charged solid sphere, non-conducting solid sphere. So let me consider a solid sphere. So this is a solid sphere, non-conducting, bad conductor, insulating, dielectric. Now it is charged uniformly. So the charge is given to it uniform. The charge is distributed uniformly. The discrete charges, if you consider, they are at equidistant. Uniform continuous charge distribution like this. So charge is distributed over it like this, right? Let the charge on the sphere be Q and the radius of the sphere is capital R. Charge of the sphere is capital Q, radius of the sphere is capital R. You know, I was telling you when we were discussing about the charge distribution, linear charge distribution, we defined linear charge density lambda. Lambda is charge per unit length, lambda Q by L. So Q is lambda L. Then when charge is spread on a surface, it is spread on a uniform surface uniformly. Then on a charged sheet, we have defined surface charge density, right? So the surface charge density is sigma, it is Q by A. So Q is equal to sigma into E for charge being spread on a surface. Now here charge is inside, it is also spread inside the sphere also. So charge spread over the surface and it is also inside the sphere. So here the charge is spread throughout the volume of the enclosure. So therefore we define volume charge density. So let the volume charge density of this sphere, volume charge density of the sphere, volume charge density, now this is rho. It is rho like this. You know, rho is equal to charge per unit volume, Q by V. So what is the charge? Volume of this sphere, we know volume of the sphere 4 by 3 pi r cube. So cross multiplying, I get the charge, the total charge on the total charge that is bound inside the sphere. The total charge of the sphere is cross multiplying the thing here. I get rho into 4 by 3 pi r cube. So the charge pertaining to the sphere, the total charge that is contained in the sphere, it is rho times 4 by 3 pi r cube. This be equation 1, right? Good. So first is charge. Then we are describing charge. We are showing the expression for the charge in terms of volume charge density. Since the charge is being distributed throughout the volume of the sphere there. Okay? Good. Now next, I have to derive the formula of the electric field at a point P. Let me consider a point P here where I have to find the electric field intensity. Let the distance of the point be smaller. Right? Now you know, whenever you need to find the electric field for this such type of charge distributions, I have given you some steps. Right? The first step is, wherever you want to find the electric field, right, imagine a Gaussian surface passing through that point. First step, imagine a symmetrical Gaussian surface with respect to the charge distribution. So I was telling you in the previous session, for various charged distributions, what should be the Gaussian surface and the direction of the electric field. I was telling you, for a point charge, the Gaussian surface is spherical and the electric lines of force are radial, right? Well, it is positive, radially outward. If it is negative, radially inward. Second, for linear charge distribution, line of charge. When you consider line of charge, then you have to consider a symmetrical cylindrical charge distribution. Cylindrical Gaussian surface. For line of charge, linear charge, the Gaussian surface should be symmetrical to this charge distribution, right? And even the lines of force, the electric lines of force are radially outward. Field will be radially outward for that also. For a sheet, when you consider a charged sheet, for a sheet like this charge sheet, then imagine a Gaussian surface such that the surface is parallel to the sheet, right? Now close it with either cylinder or a cuboid until the same thing. Imagine the other side. Symmetrically, the sheet should pass through the Gaussian surface, parallel. And what is the direction? The direction of the field is perpendicular to the, you have imagined a plane, right? With respect to the sheet, you have imagined a surface, a parallel plane surface to the sheet. Now the lines of force are normal outward to this sheet. So the lines of force emerge normally out of the plate sheet, right? Then fourth, for a sphere, you should imagine a spherical Gaussian surface. So this is a solid sphere, right? Non-conducting charge sphere. So I imagine a spherical Gaussian surface like this. First step, you have to imagine a spherical Gaussian surface. So spherical Gaussian surface, first point. Second, the Gaussian surface should be symmetrical to the charge distribution. So this is the charge. The Gaussian surface is also symmetrical, such that every point on the Gaussian surface is equidistant from it. So it is symmetrical with respect to the charge. Right? Symmetry is very important with respect to Gauss law. Imagining the Gaussian surface symmetrical to the charge is the important step while deriving the formula for the electron. Well, so I have imagined the Gaussian surface symmetrical like this, right? The Gaussian surface is passing to the point where I have to find the electric field. I have to find the electric field at point P. So the surface is passing to the point P. Now let the electric field at this point P be E, which I have to derive now. The electric field is E. Well, for a solid sphere, charge sphere, the electric lines of force are radially positive charge. It is outward, radially outward like this. The lines of force are radially outward, right? So therefore, symmetrical Gaussian surface passing through the point, direction of the electric field. It is at equidistant at all the points on the Gaussian surface. The electric field will be constant. At all the points, the field is same. Field is same with respect to this charge, right? Now imagine an area element, a small area element of area ds. Area ds. Well, the direction of the area element, I was telling you, for any surface, the direction of the area element is normal outward from the surface. Normally outward from the surface. Now, at this point, the direction of the electric field and the area element both are in same direction, parallel. The angle between them is 0. Now, so the small flux through the area element, we have to, let me consider the small flux through the area element B. The small flux through the area element d phi, it is E dot ds, right? I have already specified the small flux for non-uniform charge distribution, for non-uniform electric field. The small flux through the area element is E dot ds, so d phi is E dot ds, right? Now, if I imagine such area element E dot ds, so d phi is, apply vectors, E ds cos of the angle between the field and the area. Both are parallel, cos 0, 1. So the small flux is simply E ds. Now, if I imagine such area elements throughout the surface, Gaussian surface, over the Gaussian surface completely, through the Gaussian surface, the total flux through the Gaussian surface is the surface integral of E dot ds, right? So the total flux to the enclosed Gaussian surface is the surface integral of E dot ds. So integral E dot ds. This is equation 2. Now, so the total flux through the Gaussian surface, it is integral E dot ds like this. Now, coming to the next thing, applying Gauss law. We know next, according to Gauss law, when a Gaussian surface is imagined enclosing a charge inside it, then the total flux emerging from the Gaussian surface is directly proportional to the charge that is enclosed inside the Gaussian surface. So according to Gauss law, the equation, the total flux to the Gaussian surface is charge inside the Gaussian surface by epsilon naught. So therefore, with respect to this Gaussian surface, the total flux through the Gaussian surface is charge inside is q by epsilon naught, right? Charge inside is q by epsilon naught. Let this be equation 3. Well, you can even put this flux, total flux through the Gaussian surface, charge q is rho 4 by 3 pi r cube by epsilon naught. So 4 pi r square rho by 3 epsilon naught. Sometimes he will be asking you to find the flux enclosed inside a solid sphere when volume charge density is given. The flux enclosed inside the Gaussian surface due to a solid sphere when volume charge density is given, rho is given, it is 4 pi r cube, 4 pi r cube, yes, this is 4 pi r cube rho by 3 epsilon naught. 4 by 3 pi r cube rho charge by epsilon naught. Right? So now equating 2 and 3, applying the mathematical form of Gauss law. We know according to Gauss law, the mathematical form of Gauss law, the total flux enclosed inside the Gaussian surface integral of E dot ds is equal to the charge enclosed by epsilon naught. So equating both, I get integral total, this is surface integral of E dot ds, this is E ds. So the surface integral E ds is equal to the charge that is enclosed inside Q by epsilon naught. But E is a constant. I have imagined the Gaussian surface symmetrical to the charge distribution. So E is same at all the points of the Gaussian surface. Taking E out. So E integral ds is equal to Q by epsilon naught. Well, E, the surface, total surface area of this spherical Gaussian surface. Total surface area of a sphere 4 pi. The radius of the Gaussian surface is smaller, r square. It's Q by epsilon. Now taking this that side, I get the electric field. Electric field at the outside point. The point is outside the sphere. The electric field at the outside point due to a non-conducting charged solid sphere, insulating solid sphere, dielectric solid sphere is 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, it's capital Q by r square. Now this is the formula for the electric. The formula for the electric field due to a non-conducting charged solid sphere at any point outside the sphere, it is E, it is 1 by 4 pi epsilon naught Q by r square. Right? The magnitude of the electric field. How about the direction? If the charge inside the sphere is positive, the direction is radially outward. It is outward, radially outward, in the direction of the radius vector. Now this is radius vector r bar. So if I have to express this in terms of radius vector, for example, then the electric field at any outside point P is 1 by 4 pi epsilon naught. If I am putting in vector form E, then it's Q by r square. This is the magnitude. The direction of the electric field is in the direction of the radius vector. So now the direction is r cap, the unit vector along the radius vector r cap. So therefore electric field at any point P is 1 by 4 pi epsilon naught Q by r square. R cap is r bar by mod r. So electric field here is 1 by 4 pi epsilon naught Q into r bar by, this is r bar by r cube. This is the magnitude and that is direction. The vector form of the electric field at the outside point due to a charged non-conducting charged solid sphere. Non-conducting, insulating electric field at any outside point 1 by 4 pi epsilon naught Q by r square r bar. Well, the direction of the electric field is in the direction of the radius vector. So the electric field is 1 by 4 pi epsilon naught Q by r cube, like this. Is it? So for a non-conducting charged sphere, electric field at any outside point is like this. Well, when you consider the magnitude 1 by 4 epsilon Q by r square, electric field is inversely proportional to square of the distance. It obeys inverse square law. Well, it depends upon the amount of the charge that is contained by the sphere. The amount of charge possessed by the sphere, E proportional to Q. Well, more charge, more field, obvious. And it is inversely proportional to square of the distance. The more the distance, less the electric field. Right? If the distance is infinite, at infinite point, suppose if I consider the point to be at infinity, then the electric field at infinite point 0. R infinity, something by infinity, 0. Field here at infinite point is 0. So as the distance of the point increases, field decreases according to inverse square law. Right? Magnitude. Direction, it is radially outward in the direction of the radius. Suppose if I take the electric field at this point, it is radially outward. Here it is outward. This way, the lines of force are spread outward. They are outward normals to the Gaussian surface. And it is 1 by 4 naught Q by r cube if it is in terms of vector form. If I have to represent this in a vector form, 1 by 4 epsilon q by r square r cap. The unit vector of radius vector gives the direction, because the electric field is along the direction of the radius vector. So it is r cap. So magnitude finally 1 by 4 epsilon q by r cube r bar. Thank you. Electric field due to the solid sphere. Now considering the point on the surface, right? If I consider the electric field on the point on the surface, then what would be the electric field? Let me derive the field due to the solid sphere, charged solid sphere. If I consider the point on the surface, what would be the electric field? Now first case we have derived the formula for the electric field at the outside point. Now the electric field due to the solid sphere on the surface point of the solid sphere, charged solid sphere. So if the point P is on the surface, let the electric field be E. Now the distance of the point small r is capital R. The distance of the point is small r is capital R. Again, you have to follow the same step. Imagine a Gaussian surface just over the surface of the solid sphere, like this. Gaussian surface just over the surface of the solid sphere, right? Symmetrical to it. Then imagine a area element ds. Again the direction is same. The direction of the area element electric field both are parallel. Now the small flux through the area element d phi, it is E dot ds. Well, dot product E ds cos theta. Since both are parallel, cos 0. So small flux is E ds. Now the total flux due to this enclosure, according to the definition, it is the surface integral of E dot ds. So it is integral E ds, right? Now electric field E at all the points on the surface is same. You can even write this as the total flux is E integral ds. Let this be equation 2 now. E integral ds. Again, according to Gauss law, we know the Gauss law states that the total flux through a Gaussian enclosed Gaussian surface is equal to 1 by epsilon naught times the charge enclosed inside. Now the Gaussian surface is just over the surface of the solid sphere. It is just over the surface here. So therefore the charge inside is the charge of the sphere, q. So therefore it is q by epsilon naught. Therefore substituting, I get the total flux E integral ds is equal to charge by epsilon, equating 2 and 3 like this. Now what is the integral of surface area? If I imagine such area elements throughout the surface of the sphere there, at all the points, like if you imagine a football, the patches, white and black patches, each patch is an area element if I suppose. So considering the area of all the patches, it is the total area of the sphere there. So therefore total area of the sphere. Now the Gaussian surface is at a distance r equal to capital R. So the total area is 4 pi capital R square. It's q by epsilon naught. So taking this, E is equal to 1 by 4 pi epsilon naught q by r square. The electric field due to a charged non-conducting charged solid sphere at a distance at any point on the surface, 1 by 4 naught q is the total charge by r square, where r is the radius of the sphere there, because on the surface the distance of the point is equal to the radius of the surface. Now electric field, now if I write this in vector form, it's 1 by 4 pi epsilon naught capital Q by r square, and the direction is in the direction of the radius vector, it is r cap, right? R cap. Now so this I can write it as 1 by 4 pi epsilon naught q by r square. R cap is r bar by mod of r, but you know magnitude of r is nothing but capital R, so this is capital R. So the electric field vector 1 by 4 pi epsilon naught capital Q by r cube into r bar. The r bar is the radius vector. Well, the radius vector is same as the radius of the sphere there. So the electric field on the surface, electric field on the surface of the solid sphere, when we were considering the point outside the sphere, the distance was more than r. So in the earlier case, when the point is outside r greater than r, so the denominator was more, field is less. But on the surface, the field, radius, distance is r, so field will be more. In fact, this is the maximum field of the sphere. This is the maximum value, right? The maximum value of the field due to the charged, non-conducting charged sphere, E max, it's 1 by 4 pi epsilon naught q by r square. Sometimes he'll be just asking you to find the maximum. He doesn't specify the point. He'll say a charged non-conducting sphere is charged with a charge q is equal to some 10 microcoulombs. Then the radius of the sphere is so and so 10 centimeters. What is the maximum electric field produced by the sphere? So the maximum electric field produced by the sphere is, the field is maximum on the surface of the sphere. So he is indirectly asking you to find the electric field on the surface. So electric field on the surface point, at any point on the surface, magnitude is 1 by 4 epsilon q by r square. This is the maximum electric field due to the solid sphere, right? Charged solid sphere. Good, right? So this way it is. This is the application for a non-conducting charged solid sphere. Non-conducting or insulating or dielectric, please remember the question can be in any form, right? You should be able to make out. So it's either dielectric, non-conducting or insulating charged solid sphere, so of radius capital R. The total volume charge density is rho and the total charge is Q. Now let us put the formula for the electric field at all the various points in one shot, one diagram, in one display, right? So the electric field at various points due to the sphere at different points. Let me take the field due to this at different points in all the terms. So the first point at infinity. Second, at an outside point, P. Second point it is, this is the second point. Third, on the surface point, on the surface, third point is surface point like this. Fourth, an inside point, and fifth at the center. So the electric field due to this at different points. Let us write down the electric field at all the points in all terms, right? Now we know for any charge at infinity the electric field is zero, whether it is a point charge sheet, whether it is a point charge for a solid sphere, hollow sphere, dipole, anything. At infinite distance the electric field is zero, right? Okay. Now coming to the outside point, let the outside point be at a distance d, so r is equal to d. So the field at the outside point. So the electric field at any outside point P, E, we have derived E is equal to 1 by 4 pi epsilon naught. The charge on the sphere, the total charge, this is a non-conducting charged sphere, charged uniformly. Uniform charge distribution is being spread over it. Then the total charge Q by d square. This is the magnitude of the electric field at the outside point. So the magnitude of the electric field at the outside point for a non-conducting charged sphere when charge Q is given is 1 by 4 epsilon q by d square. Same question he will ask you if it is given in terms of volume charge density, right? Volume charge density rho. If rho is given, you know rho is charge per volume, cross multiply. So charge Q is rho into 4 by 3 pi r cube it is. 4 by 3 pi r cube. So substituting electric field at any outside point. So E outside point is 1 by 4 pi epsilon naught. Q I shall substitute it as 4 by 3 pi r cube, right? Sorry, 4 by 3 pi capital R. The radius of the sphere given is capital R. So radius of the sphere is capital R. 4 by 3 pi capital R cube into Q by d square. 4 pi cancel. So you get E at the outside point is capital Q R cube. Sorry, rho it is. 4 by 3 pi r cube rho it is. So therefore rho r cube by, now this 3 comes to the denominator, 3 epsilon naught d square. So electric field due to a non-conducting charged sphere at any outside point. If charge is given 1 by 4 epsilon q by d square. If volume charge density rho is given, I am substituting for charge q. Q is rho times 4 by 3 pi r cube. So here if I substitute rho times 4 by 3 pi r cube, 4 pi gets cancelled. So I get rho r cube by 3 remains in the denominator, 3 epsilon naught d square. So the electric field, magnitude of the electric field at any outside point is like this. Is it? So 1 by 4 epsilon q by d square or rho r cube by 3 epsilon naught d square. Is it? Suppose if he specifies, if he is asking to find this in vector form at the outside point, E outside vector form, then it's 1 by 4 pi epsilon naught q by d square. Well, the direction of this radius vector, r bar. Well, r magnitude is d, right? R, so it is r cap, radius vector in this direction. R is equal to d, the magnitude is d, but the vector is r cap like this, right? You can even write this as r bar by mod r. Mod r is d, so d cube you will get like this. So 1 by 4 epsilon q by d cube r is the vector showing the radius vector showing from center to this point. Is it? The magnitude of r is d, but the vector is r bar like this. So this way you can represent. Even in this form also, here also, E in terms of this, then vector form, it's rho r cube by 3 epsilon naught d square into the vector, radius vector. If the vector is r, it is r bar, r cap. Well, if I imagine it as d, then it is d cap. Whichever way you consider, you can take. Right? It is our convention. If I imagine this vector as r, then it is r cap. Or if it is d, it's d cap. Or if I put it in vector d bar by mod d, so then it becomes d cube. Rho r cube by 3 epsilon d cube d bar, where d bar is the displacement vector from point to there. Okay, it is a radius vector. This way, in vector form you can represent. Now here, at the outside point, the electric field is inversely proportional to square of the distance. Inversely proportional to square of the distance. Good. So this is regarding the second point. Coming to the third point, the electric field at the third point. At the surface point here, the electric field at the surface point. Well, the formula, charge is q, distance. Now the distance of the point D is capital R. So the formula becomes 1 by 4 pi epsilon q by D is capital R. So it is r square. It is r square. Vector form into r cap. Well, if he is asking you in terms of volume charge density, then the electric field on the surface will be 1 by 4 pi epsilon naught. Charge q, I am substituting it as rho into 4 by 3 pi r cube by, it is r square. 4 pi, even r square also cancels, you get r. So electric field on the surface point is rho r by 3 epsilon naught. This is the electric field. So field on the surface point of this non-conducting charged sphere, so it's solid sphere, it's rho r by 3 epsilon naught. You know, this is the maximum value. It's the maximum electric field I was telling you. So maximum value, rho r by 3 epsilon naught. Rho is a constant, r is a constant, all are constant, it's constant. So at any point on the surface, the electric field is a constant. Maximum value is constant, magnitude is same. Well, direction is outward normal, right? It is along the radius vector, r bar. If the vector is represented as r bar, so rho capital R by 3 epsilon naught, I am representing the vector as r bar, so it will be r cap. Is it r cap? Or it is r bar by mod r. If I represent this E bar, it's rho by 3 epsilon naught capital R, it's r bar by mod, magnitude is r gets cancelled. This is in vector form. So this way you can write down the electric field in terms of charge, in terms of linear charge density, in terms vector form, all the forms. I am putting all the things in one display. Please remember, okay? Now coming to the next point, inside point. Inside point at a distance smaller. Right here at this inside point, electric field at the inside point here. Then, so what is the electric field at the inside point? Let me put it here. I am writing the electric field at inside point here. Very important, you should. So, rho is like this. Let me write down the charge from this. It's rho into 4 by 3 pi capital R cube. Please remember this, right? Now, electric field at inside point. So, we have deduced the formula for the electric field inside the, at the point inside the charger, non-conducting charger sphere. It is Q capital R by R cube. Right, so it is Q by R cube into capital R. So the electric field is at any inside point 1 by 4 epsilon Q R by R cube it is it? Well, in terms of volume charge density, if I have to specify at any inside point, it's 1 by 4 pi epsilon naught. Now substitute charge, volume charge density is Q by V. Q is rho into 4 by 3 pi R cube. So rho into 4 by 3 pi R cube into small r by R cube. 4 pi R cube, 4 pi R cube cancel. So this is rho R by 3 epsilon. It's rho R by 3 epsilon naught. Suppose if I want to specify in vector form, E in vector form. So it's 1 by 4 pi epsilon naught capital Q into R by R cube times R cap. It is vector. R cap. Or this I can write as R bar by mod R. Well, R gets cancelled. Vector form. Even here also it is rho. Vector form, if I have to specify in vector form, E bar, it's rho R by 3 epsilon naught times R cap. Or it is rho R by 3 epsilon naught. What is R cap? R bar by mod R. R gets cancelled. So rho by 3 epsilon naught R bar or rho R by 3 epsilon naught R cap, is it in vector form at an inside point. So inside point, the electric field is proportional to R. At any inside point, it is directly proportional to R. On the surface capital R, here it is inversely proportional to square of the distance. You have to know the proportionality. How does the field vary with the distance? Outside point, it is square of the distance. Well, so these are the formulas for the electric field at any inside point it is. Inside point, right? So, field at inside point 1 by 4 pi epsilon naught capital Q small r by capital R cube, or it is rho R by 3 epsilon naught. How about the electric field at the center? E at the center. You know, at the center small r is 0. So put R 0 here. So the field is equal to 0. At the center field is 0. So if I show this variation of the electric field in the form of a graph, right? Graphical representation. Now please look. This is the point at small r is capital R. Inside the point, at the center field is 0. So the graph starts from 0. Electric field varying with the distance like this. So how does the graph vary? At the center electric field is 0. Here it is 0. Inside, at any inside point, electric field is directly proportional to R. So for anything, when it is directly proportional, it's a straight line passing through the origin. For all the inside points, the electric field is directly proportional. Here, the electric field on the surface, so this is the electric field on the surface, that is maximum electric field, that's maximum electric field, it's rho capital R by 3 epsilon. And at outside point, it is proportional to distance by inverse square law. So the graph varies a steep curve like this. Graph is a steep curve which touches the axis at infinity. It touches the axis at infinity like this. So the graphical variation of the electric field for the positive charge, the electric field is outward normal like this. Had it been negative, it would be the downward direction. Right? For negative charge, the field will be towards left, that is minus. Then the same graph comes to the fourth quadrant. For positive charge, the graphical variation is like this. Okay? Thank you. So yeah.